Austrian people.
I'd like to start off here by introducing Gillian Larkin, the youngest of his 5 daughters and the one most like him as well, and tell us a little bit about the history here of the Larkin Lectures and a bit more about her family.
You don't want to miss out on that.
Thanks very much. Just out of curiosity, how many of you here are your first Larkin Lecture? Oh, fantastic. Well, welcome. When I do my little family piece to introduce this lecture, I like to tell a story that gives those of you here today some sort of idea who my father was. He's been gone for over 20 years now, and many, if not most of you, never met him. And the little slideshow that's been playing gives you a bit of an idea, but I know there's a story, so here it is. At the 1992 UBC publication ceremony, my father received an honorary DSc, and then he gave a short address to the science crowd. He started out by talking about how he and my mom had graduated with biology degrees from the University of Saskatchewan on a spring day in 1946, just like those students in the audience in 1992. He talked about how his head was stuffed full of the latest and greatest knowledge, and he figured that he was set for life. Then a few years later, someone discovered DNA. He hadn't had any lectures on that. Then faster computers and new software came along. He hadn't even had any courses on that. He continued with similar instances of new findings in geology and chemistry, and in his mind, all of these examples served to demonstrate that not only were there things coming along that they hadn't been taught, some of the things that they had learned were just plain wrong. So he wrote to the U of S asking for a refund. Unfortunately, the university didn't agree. They came back saying they couldn't be responsible for post-graduation discoveries, or worse to that effect. He then went on to tell the audience that unfortunately UBC had the same backward policy. He proceeded to then address President David Strangley directly, asking for change. He pointed out that the scientific literature was expanding at an astronomical rate. The literature was doubling every 8 years, and in some disciplines like molecular biology, it was doubling every 18 months. This meant that more than 90% of what would be known by the year 2000, only 8 years away, had not yet been discovered. The figures are likely even more overwhelming today. But he had a solution. He suggested that graduating students be sent forth into the world with best before labels that indicated when their education expired. In order to be relabeled, students had to come back for refresher courses. Thus, he argued that graduation diplomas should come with detachable coupons for these refresher courses, redeemable, say, within 100 years or so of graduation date. All kidding aside, he then delivered his key message. He pointed out that many people in society don't have the opportunity to go to university, and many of those in university don't take science. As science graduates, that class was joining less than 2% of the population of Canada and far, far less than 1% of the population of the world. He maintained that it was the societal responsibility of this elite group to use their powers of analysis to weigh the evidence and speak up when others sought to fool the public, be it for fame, fortune, or political gain. He firmly believed that the most important thing provided by a university education is the thirst for more knowledge to keep you informed throughout your life. And I think a lot of those sentiments, even though they're only 20 years old today, are still relevant today. Indeed, my father was more than a great scientist, teacher, or administrator. He was, above all, a great student. This lecture series meant a lot to my father when it was established, and it continues to be very special to our family. First, it honors and celebrates my father's excellence in this medium. When my father lectured, he was energetic, engaging, and witty, with a contagious enthusiasm for science and learning that infected his audience. Second, it provides the opportunity for the members of the Institute for Oceans and Fisheries community and beyond to interact face-to-face with scientists of international renown. Reading someone's books and papers does not in the least compare with meeting them in person and engaging with them directly. And thanks to this lecture series, 13 such experts have come to share their passion for fishery science. On behalf of my sisters, I would like to thank you all for coming here today in celebration of lifelong learning. And I thank Dr. Fulton for accepting the invitation to be the 14th Larkin Lectures.
Beth is all dressed up today, and that's not normal for Beth. Beth's a farm girl. She grew up on a real small farm in New South Wales in Australia, near Canberra, and she lives on a farm today with farm animals and so on. But I've never seen her so nicely dressed. Most of you know me, and you know I'm not easy to intimidate. Beth Fulton intimidates me. She's probably the smartest, most knowledgeable person I've ever met. She's an amazing character. While she was growing up, just as she was finishing high school, she went off to Britain for a term of study in Britain and worked as a shooter for big game hunters. Rich guys that go around shooting red deer and things like that. When they couldn't hit them, Beth was there to shoot the deer for them. Imagine that. She went to James Cook Uni for undergraduate, and she got a double honors degree in mathematics and marine biology. She went on to do her PhD at the University of Tasmania. It was a remarkable thesis. I was her external examiner. And I didn't understand 2/3 of it, so I had to take my comments. And since then, she's been at CSIRO as an ecosystem modeler and policy analyst for conservation. She's received numerous awards, including being a few fellow in marine conservation, and perhaps best, she received the Australian Science Minister's Prize for Life Scientist of the Year in 2007. Her ecosystem modeling work that you hear about is considered kind of gold standard by agencies around the world now for approaching complex ecosystem management problems. And I hope she's going to tell you a little about that in a way that you'll understand better than I do.
Well, that's a very embarrassing introduction to have to live up to. And also, hopefully I can speak as well as the person I'm doing this in the honour of. I'd like to start off with the tradition from my mob down in Australia. I'm Indigenous partly by descent, and we thank the elders of the land that we meet on when we go into someone else's country. So I'd like to thank the elders past, present and future for the land that we meet on today. They have wisdom to share with us about how the world works. Their geological knowledge, their historical knowledge is something that we can all learn from, which is really important because the way that we manage the world is by looking into the past. It's like driving by looking into the rear view mirror. You can only collect data on the world behind you. You can't collect data on the world that you're about to get to. So how do you know that you haven't driven off the main highway onto a dirt track? More importantly, quite often, that rear view mirror is very fuzzy. So we don't really know where we're actually going. So that's actually how the traditional languages around the world, I'm yet to find one traditional language that doesn't talk about time that way. So they walk backwards into the future, looking into the past about where they want to be, what the world's telling them. But about 2,000 years ago, the Romans changed that. They changed the way that they talked about the world because they knew that the world that they lived in had become so complex that the past was no longer a good guide to the challenges that faced them. And we're pretty much in the same situation. So these are from geological ice cores, the pH and the temperature profiles over the last 80 million years. The solid dots are the projections into the future. So we really are changing the world very, very quickly. So processes that I could write off as fixed variables when I first started doing mathematical ecology 25 years ago are now happening in real time. So evolution is an ecological process that we have to account for now. There's a whole bunch of scales and processes from the microbial and the parasites right up that we never had to worry about before. So our cheats, our simplifications that we used in the past aren't working very well anymore because we've pushed the system to a place where those assumptions break. And one of those assumptions by the big wide world out there is that fishing is the only thing that affects the ocean. So we just have to fix that. These are all photos from China and Europe. That's not only the things that happen in the ocean anymore. So the agrarian revolution, the industrial revolution, the great acceleration of the 1950s are all happening simultaneously in the ocean right now. There's exponential growth in all of those uses of the ocean. So how do we understand how those things are connected, how they're going to evolve into the future? That gets beyond the kind of models and approaches we've been able to use in the past. But it's not a problem that's new to us. People have been grappling with how to manage fisheries alone for 5,000 years. So China actually has the original documents that the first known fisheries minister on the planet put out. And every single management lever that we have today, gear management, quotas, spatial management, seasonal closures, they're all in there. So in 5,000 years, we kind of haven't learnt anything. It has passed through various different levels of control, but we really are struggling to find new ways to do things. And we can see that in the way that we've evolved our interaction with the oceans. We've started from single species to realising we're actually interacting with multiple species and into all of the other actors in the system. And our management systems and our modelling systems all reflect that too, where you go from single stocks up to full integrated models. So I work at all of those different scales, but more recently I've had to take on trying to tackle how you get all of those sectors working together. And I would have to say that while we have strategic looking models that can sort of tell you the general pathways, we can't yet do classical assessments all the way up. We're struggling, particularly at that top level, to get a handle on how to give useful short-term advice on those big interacting systems. Mainly because, from a manager's point of view, you want a maximum set of outcomes for a minimum set of intervention, or in fisheries parlance, you want minimum sustainable whinge, which is minimum sustainable upset, basically. So how do you go about actually providing that? Well, if you're a manager, you're happy to think about this interaction, but in reality, what's happening is that you have to, in reality, deal with all of these interactions as well, which is why they look a little bit distressed when you say you have to get away from just the fish and the fishermen. More importantly, from a scientific perspective, from a mathematical perspective, the characteristics of those really complex systems are all of the things that we're really poor at being able to do. So nonlinearity, path dependence, being adaptive, trade-offs for both mathematical reasons but actually psychological reasons. That's not a space that we work well in. So it's a sensible initial reaction to start with something simpler. But in the world that we live in, where we're pushing the boundaries, we can no longer just stop there. We have to keep going further. My computer's decided it's going on strike. But to give you a comparison, it's easy and fun to carry one person across the water. Gets a bit more challenging when there's two. Once you get bigger, you've got to start different technology, basically. And they can start fairly rudimentary, but you can build up the technological sophistication as you go through time. But you will eventually find the bounds of any single set approach. So you've always got to be looking for new ways of tackling the same questions. So that's been realised in the management side of things, where they've got lots of different ways for calling for the same thing. It's all taking a systems approach to management. Lots of people get caught up on what's the difference between an ecosystem approach and ecosystem-based, and the easiest way to think about it is an ecosystem approach is working up. You start with a single species and you add in the things that might be affecting that species to give it that bigger contextual view. Whereas ecosystem-based is you start at the top with the system view and then you hierarchically go down to what's impacting things at lower levels. Otherwise, they're really the same thing. They're taking that systems view to the question. So it really involves balancing and juggling a whole bunch of things and trying to doing the planning, the monitoring, the decision making that we all have to do. It's about juggling those trade-offs and those different components. So having economics and social and cultural objectives met within those sensible ecosystem bounds. Now, we see that actually defined in international law, where it recognises that it has to be a societal choice and it has to be about meeting what society needs, but also recognising that there's some inherent ecosystem structure and function that can do that. What that actually looks like in different systems of the world will differ because they have different cultural needs. So there'll be some unifying ecological boundaries that we can rely on, but in actuality you're going to have a very different view in Australia, where there's a strong conservation ethic, versus a place where they're just struggling with food security. It's not my place to come in and tell them one or right's wrong. I can just say, here's the bounds of what works. Then it's a local discussion about what they want within that. And I have achieved far greater ability to get that across by respecting that than coming in and saying, no, this is the way you have to do things. Now, if we look into that might be the big vision. If you look into the actual national laws, there's a very strong focus on maximum sustainable yield. So for a single species fishery that's very clean, just takes one species, that's actually not a bad approach to take. But the reality is that the majority of fisheries in the world aren't that clean. So at the next stop you might have what's called a mixed species fisheries, where there's no trophic interactions between the species you're catching, but you're catching more than one species at a time. So it's what they call technical interactions, is they get caught with the same gear. Even in that situation, you can't deliver maximum sustainable yield for both species. You'll ultimately typically have at least one species that acts like a brake, a choke in the system. You can't get enough of it to supply the others. So you either let it disappear from the system or you don't take as much catch, and that's a conversation to be had. When you get into multi-species fisheries, such as in lots of tropical places, but also in southeast Australia, so we have 400 species that we catch. 34 of those are main target species that we have to try and manage explicitly. There's no way that we can have maximum sustainable yield for all of those species simultaneously. It's just not possible, because the maximum sustainable yield for the prey species kind of assumes that there's no predators and vice versa, like it's all over the place. You literally can't have them all together. So we've legally set ourselves up for something that we can't do, which kind of seems a little bit silly. But how did we get there? So basically in the 1850s, the MSY concept came up in Germany. By the time you get to the 1930s, they needed something to manage their system. So they started off by having that question. It happened to coincide with a whole bunch of geopolitics where they wanted some rules. So it got written into the laws at that point. Now you get to the 1970s and we're already recognising that it's not something that actually works. By the 1994, its practicality is being questioned. By the time we get into 2000s, we're realising it does significant damage to whole ecosystems. But as late as 2016, it's still being put into new laws. So the legal side of the world hasn't caught up with the science side of the world. So we're saying, hey, it doesn't work. The legal guys are going, no, they used it over there, we'll use that too. So they don't always understand why they're the downsides or that kind of thing. They're just adopting what's being used elsewhere. So why do they do that? How do we get there? So it started off with a fundamental debate back in the 1800s about, are natural resources limited? And they got to an answer on that after the First World War. Yeah, okay, they are limited. Right, okay, first great fishing experiment done. So then they got into a debate about the kinds of controls that you have in a system. And in reality, those debates haven't actually ever ended. They just kept going, but it was a good idea to keep the technology meant that they were literally doing these by hand largely, so you wanted to start that simple. So it did work for some species. It works much better than not doing anything. That's been shown, so it's a good first start. And then you get this divergence that I have personally experienced, where I've had single species stock assessment guys go, no, we just need to get our model perfectly right first and then we'll worry about the ecosystem stuff. When they're trying to fit to the very properties of non-stationary natural mortality or environmental change that the ecosystem model is doing. So they're killing themselves trying to deliver something that is because they're missing processes that haven't come across. The other one I love is, yours is just a model. Actually, so is yours. So, it's about trying to keep perspective and have both views come into the room. Then you get into the question of, okay, we accept we need it, but until you can tell me exactly how to do it, we're not going to even try. So they're not willing to do that trial and error phase that they were for single species as they've gone through time, but they shy away from ecosystems. So they're very risk averse. You can't really blame them. It's a lot more legal these days, but it is a frustration that they won't do that learning process. They're not willing to try it anyway. It's not actually political will that's the stop. I've worked with many fisheries managers and politicians and policymakers around the world. They just don't know how to get across that divide, so we have to find some way to help them do that. The other part of what's happened is called path dependency. So the decisions that happen in the past can narrow down the possibilities. So you can have perfectly good options that exist, but for various reasons they don't get locked in, and the thing that does then becomes self-reinforcing. So these unexplored options are called amistics after the Amish. Actually, the science fiction writers have been talking about this for a while, because in the 1960s we already had the technology for flying cars, hypersprays, renewable energy, but we didn't pick them up. They didn't reinforce the technologies that were already there, so we put them to the side. And at least one of those is starting to get legs now, but I still have to face a big needle if I want a vaccination. So some of the other technologies haven't quite taken off yet. So the way that path dependency works is that there's kind of three major conditions that see it coming in the first place. One is it's the best possible option at the time, which MSY was. So that's how it got there in the first place. There's other ones where it's a bit of social influence. Okay, he's using it, and he's like a trendsetter, so I'll be doing that as well. Admittedly, the porn industry has directed much of our audiovisual technology for probably the last 100 years, which is a little bit embarrassing as a human species, but it's where to look for technology of the future. And there's also the actual stochasticity, what happened to get some attention at the time. Once something gets locked in, there becomes a whole bunch of other things that happen. So people are used to having it. So all of us type on keyboards. The majority of us using an English keyboard still have a QWERTY keyboard. It's been decades since we had to worry about keys hitting each other. Why do we still use an inefficient keyboard? Because we're all taught to type on this keyboard set, and it's easy to produce, and everybody's set up to produce it. If anyone has ever seen my laptop after at least 18 months of use, I've worn the keys off, so I remapped them to something that's comfortable for me to type, which is not QWERTY at all. But anyone who comes to try and steal my laptop is going to get an awful shock when they just get gibberish out the other side. The switching costs of doing things, of using new technologies, of using different approaches, is because you get invested in those approaches. You know what they are. You keep going over the same things. And then it gets built into the legal constraints. It's just an assumed thing. So it becomes a self-reinforcing. You can't get out of it until it hits the wall. And then you get a new option. And climate change and global change is that option for us. It's driven home to us that the system that we have today isn't working very well. It's not coping. So we can, instead of being horrified by the challenges that we face, we can embrace them. Everybody's mobile phone that they have in their pocket in this room, that's more powerful than 90% of the computers put together when I graduated from my PhD. You know, my watch has more power than we got to the moon on. So we certainly have computing power galore to tackle these questions. So in looking for that new option, we can put in options that can be adaptive, that can have that ecosystem approach. But we need to do it in a way that's conscious of this lock-in problem, so we don't lock ourselves into a new technology that's also going to be subservient in years to come. Now, part of the reason that that happens, and another reason that we're still using MSY, is the human brain is a very slow thing to learn. Our greatest example of that is that when you're about 11 or 12, your brain unwires itself and moves everything that it learnt from the front to the back of your brain to clear up space for new learning. So that's why teenagers look like they have no self-control. They literally have no self-control. It's the first thing unwired and it's the last thing rewired. So leaving your teenager in charge of your house for the weekend, would you leave him in charge of your $100,000 bank account? No, then don't leave him in charge of your house because he has no self-control. I have learnt that. I have 2 sons and a daughter. I've learnt that the hard way. So that's when you have, so the lawyers, for instance, they're going to think of MSY because it's now embedded in the back of their brain. It's the ecosystem-based approach is at the front of their brain. It's an effort to remember to do it. You instinctively go to the things at the back of your brain. That's easier to do. So getting it to transition is about 15 to 25 years of saying the same thing over and over again until it's embedded. So that's why you can't give up. There's a whole bunch of other cognitive biases that we have as well. So that was well done, Beth. Do that. Oh, there we go. So if you ever want to read a very large but exciting book, there's a book by Daniel Kahneman called Thinking Fast and Slow. So it explains how you think. And if you're anything like me, you'll spend half your time going, oh, I don't do that. Oh, yes, I do that. So on the short side of things, we think intuitively. So our very fastest decisions are usually made intuitively without thinking. We're calling on the back part of our brain. That's a whole bunch of rules of thumb which don't actually usually work anymore. You can have a more deliberative process, but it's energy intensive. So we don't actually like to do it. We have to physically get ourselves to think about it. Ironically, the best way to do that is to make yourself sad. We engage that part of our brain much more easily when we're sad. And again, rather embarrassingly as a human species, if you put a pencil under your nose, it forces your face to frown and it triggers that brain set. So if you really need to think, put a pencil under your nose. That's how silly the brain is, to be honest. There's a whole bunch of things that we do. So for instance, we do this thing called association. So if I was suddenly to show you a whole bunch of small children running around, you would walk out of this room measurably faster, not just because of small children, but for the association reason, than if I showed you a whole bunch of old people along on walkers. Our brain resets and goes, okay, we need to walk slowly if we're around old people. More ridiculously, if you took out, in our case in Australia, a Medicare card, in America it would be your national health card or whatever, and you looked at that number and it happened to end up with a 999 on the end, and then you went to bid on a house, you would be willing to pay more for that house because you'd recently seen a large number. That's how silly our brain is. We do associations that don't actually mean anything, which means that we like to tell ourselves stories of how the world works. We feel more comfortable if we can tell ourselves a nice little story about how the world works, and particularly one that makes us feel happy. We don't like facts that make us feel sad, and we tend to ignore them. The other thing we do is called substitution. When you're faced with a really complicated question, your brain just substitutes in an easier one. How do I manage a whole ecosystem? Oh, I can do a single species with MSY. That's the way that that kind of thing happens. And when you think about the kind of things that have been put forward around managing systems over just even the course of my career, there's been some pretty vitriolic debates at times about what's the best way to manage a fishery. So as a policy maker on the outside, faced with all that complexity, they're like, yeah, we'll just go back to MSY, that's already in the laws. So they substitute that easier question. The other thing that happens is we have a whole bunch of fallacies and odds that we do. So we don't like if we're going to lose out on something. We do like it, we don't like embracing stochasticity. We like the mean of things. We work off simple, small sample sizes. We leap onto dramatic things. So after 9/11, they surveyed a large part of the American population. They all thought they were going to die in a terrorist attack, but didn't think firearms or cars were something to worry about, when if you look at the actual statistics of death, it was well and truly around the other way. We dramatise our world. I suffer, as my three colleagues in the room will tell you, from optimism bias. Every day I think I'm going to get loads more done than I actually physically could ever do. Confirmation bias is something that a lot of people suffer from, which is you only listen to facts that you already know and you try to filter out things that disagree with your vision of the world, which means that ecosystem-based management is really hard because it's actually all about trade-offs, and trade-offs play into a lot of those aversions that we have. So they forcibly make you look at the fact you're going to lose things because you have to trade them off. So that triggers our loss aversion. It often makes us choose between things that aren't easy to trade off. So it's hard to give you a fisheries example here, but an easy example is to say you wouldn't put a dollar price on the life of a child. That's what they call a taboo trade-off. You're trying to trade off a secular thing for something that's held sacred to you. That just makes them completely inflexible. So if you're working with an Indigenous population that has a cultural tie to a location, and you try to be helpful by saying, look, we'll compensate you for them, that's just going to make them enraged because you've just caused a secular versus a sacred trade-off. It just makes them completely inflexible. Humans also really hate uncertainty and ambiguity, and looking at MRIs of people presented with that, it triggers the same part of the brain as suspicion. What are you hiding from me? So you get suspicious. So the initial reaction is, I want more information, so they don't do anything, or they defer. You know, we see that over and over again. Oh, I just want some more information first. It's not just that they're stalling for time, it's an actual mental response to being presented with ambiguity. And they also feel deceived. So none of those things about ecosystem-based management are actually going to make you feel good, even if it's the best way of doing things. So how do we get from managers, or coders in my case, that look like that, to ones that actually look more thoughtful, or in the case of laws, I've just lost myself. The case of laws, ones that are sort of band-aid stack-up of different laws on top of each other trying to patchwork things, versus something that takes a more integrated approach. So you can actually make the, I've done it again. You can, I think I'd learn, wouldn't you? So you can actually make use of those same psychology. So this is an example from a really smart young lady in Tasmania called Mary Mackay. So legal fish in this fishery are at 20 centimetres. But what she did was hand out to small children in Australia this ruler, because lots of people take their small children fishing with them. So yes, you could keep this one, but do you really want to? All the way up to, yeah, okay, this is ones you really want to be keeping, okay? And the average size of fish being landed effectively doubled within a 3 to 4 month period because people are susceptible. The other thing she did was she put pictures of large fish at the landing sites and people started throwing away live, thankfully, not dead, the fish that were smaller than that. So you can use that same psychology to help nudge people in a more gentle direction. I, for instance, have a picture of myself in a swimsuit on the front of my fridge to remind me why I really shouldn't have ice cream after dinner. About 10 years ago, I had a little bit of a revelation that helped me start to think about ecosystem-based management in a slightly different way. I was a part of a large working group trying to come to consensus between conservation and fisheries about the status of the world fish stocks. And everybody in that wanted the classical hump for exploitation, like the red hump there. And I couldn't get it out of half of the ecosystems in the world. So I kind of said, nice girl, Beth, go sit in the corner till you can actually be helpful. So I looked at the different, it was a lot of the multi-species fisheries that had this big flat top, often in tropical systems. Unbeknownst to me, about 30 or 40 years ago, 30 years ago actually would be, there was a bunch of very smart people that sat down and had decided it was to do with ecosystem type. So I went away and I was trying to model this. I was like, okay, let's apply the same fishing pressure to all of these different, so I had 40 odd ecosystem models of different kinds, and I just fished them all in the same kind of ways. And I expected to get back that the tropical system had the flat top and the temperate system had the sharp shape, and then I could dig into the model as to why the different ecosystems worked a different way. And I can very distinctly remember the day I bowled into my office to open up the runs that had happened over the last week, and I was like, holy crap, it's the way we fish it. At least in model world, it's the way we fish an ecosystem that derives those two different shapes, not something that's a property of the ecosystem itself. So really selective fisheries were causing this sharp pace, whereas the multi-species, the flat top, take everything at once fisheries, were producing these big flat tops. Now that's not to say that you can go holus bolus and fish a whole ecosystem madly. You still have to be sensible about what you do, but it was telling some extra things to think about. Particularly given that under that kind of selective fishing, it appeared that you forced species out of the system much faster than if you were fishing things much more evenly. And I was trying to understand what that was about. But this is a good example of where modelling started to open up some eyes about what's actually happening. Let's see if I can get my computer to... There we go. So models are really good at being able to filter out, give some internal consistency to their thinking. So humans can come up with options of the future that just aren't possible, whereas models can say, yeah, okay, this is what is possible. What do you actually want out of the world? What's the most probable? And then how do we get from one to the other? And that's largely what my last 25 years of my life has been using models to help people have that conversation. Because humans can't do in our heads what this artist has done, which is go from the past to the future in one smooth transition. We think about the past, the present and the future as three distinct pictures, and they can be internally disconnected. They don't follow the same rules. We don't have a smooth flow from one to the other. So that's where models can help make sure that in transitioning from the present into the future, that we don't put forward futures that aren't actually possible. And that's why there's different kinds of models that each have their own value. So there's some that are just around understanding how a system is put together, some that help you make decisions year to year or season to season, and some that are about that big picture thinking about where you want to do things into the future. Now, I work a lot with the last kind of model, and over the last 20 years there's been an evolution in the models that I do. I started off in my enormous thesis that Carl lovingly reminded me of today, and my mother actually uses to keep her kitchen door open. She hadn't realised I was going to drop in once, and it was there, and then she admitted that's really what she uses it for. It is about this thick, you can't blame her. So the idea was how you build the ecological side from the environment into the food web with some representation of fisheries. From there we got into representing the management strategy evaluation cycles. So how do you represent the scientific collection of data, the assessment process and the management process back into the fisheries, because funnily enough fishermen just don't do exactly what managers say. How is that filtered through the human side of things? But more recently into all of those other uses of the coastal and ocean zones, including societal cultural responses, lobbying, and how you make those kind of systems stable, because without the right kind of connections within them, you can actually have a very unstable system. It's also about how to do modelling well. It's not about representing every tiny little detail of the world you're trying to reproduce. So that's clearly a bird, but it's not perfectly anatomically correct. It's got the essence of a bird. And that's what you're trying to do with a good model, to capture the essence of the system, the question that you're asking, without getting caught up in infinite detail. And that involves bringing together different ideas from different disciplines, but also having a range of models. Billy has coined a phrase that I really love. Models are not a religion, you can have more than one. Okay, so you can have lots of different ways of looking at the same question. And in my group in Australia, that's what we've done. We've drawn on different methods from around the world to get together a toolbox of approaches for looking at the same question. So you've got statistical distributions. We don't collect a lot of data in Australia. We're kind of the most developing nation on the planet. We have multi-species fisheries, one marine science vessel for the whole of Australia, no surveys. You know, it's a very cut down vision of the world. So we can, however, the oceanographers are way ahead of us. Somehow they managed to get crap loads of data. So if we can proxy to their data, that might tell us about what the system is actually doing. Another one is to learn from people like William and actually use physiological tolerance just to say, okay, species like these kind of conditions, where are those conditions going to be now and into the future? There's size-based methods, which is a shortcut for describing marine world, where there are some size relationships obvious in observations. There are some tweaks to make that work, but it's a great way of very rapidly summarising what's happening. There's the trophic world that EcoPath with EcoSim has popularised so much. It's the most common approach, which is the most obvious one to humans, particularly my sons, as who are very food oriented. It's who eat who. I can tell you, however, EcoPath with EcoSim is a great way of reproducing the Lord of the Rings dynamics. My kids actually used to do that to entertain themselves when they couldn't get me out of the office. Another way is to take this intermediate approach, which is to pick the key parts of a system and just look at how they're connected and how they'll move into the future, at the minimum realistic approach. There's the Bayesian approaches, which are saying if I'm in, and often fed by experts, you don't need lots of quantitative values for this necessarily. So if I'm in this kind of state, what's the probability I'll transition to that state, so you can understand how the system evolves. But you can go one step further with qualitative information alone. That's just positive and negative interactions. You can map out the conceptual understanding of a system and then start to press on that system and say, where is it stable? If I press on this bit, which bits come up and down? And you can literally do that in an hour and a half with people to tease out very rapidly how things are working. Then you've got the last kind of version that I have spent a lot of my life on, which is learning from all of those approaches, or stealing from all of those approaches, to represent the system. There's not just one way to describe a system. The world isn't little cookie cutter versions. There's different currencies and different methods to represent a habitat versus a fish versus a human. So marry them together to actually deliver, and even through a life history, you might want different approaches for different parts of a life history. So how do you marry those kind of things together? And the latest part of that, and I think a technology, if my computer could ever keep up, is one that I worked on with a grad student of mine who's retired to become a curtain hanger, so that probably says something about my teaching capacity. But he did that. He was much, much older than me. He was actually retirement age. It was one of those people that did his PhD as the last thing of his career rather than the first. But he showed mathematically how to do this, which is really cool. You have one set of one model that starts off as an ODE, and then as it interacts with an event, it actually itself morphs down to being an individual-based model that interacts with that event. Then as it comes out the other side, it morphs back into a statistical model that takes those properties into partial differential equations. So it uses every form of model, but it self-morphs from one to the other as it interacts with systems where the previous kind of model couldn't cope with that information, but as soon as it's got through the event, it tries to simplify back for computational reasons. So it morphs its own shape in the way that it needs. So we've been doing that in time and space for a while, but this is actually about the mathematics of how you do the different steps itself. So that was a PhD that made my ears bleed, but it was very, very exciting to see. So we're now trying to get other people to do it rather than just hang curtains, as Randall's decided to do. On the very opposite flip side of that is how do we get back to that assessment question? So all of those big models are fine for asking the big questions, but on a day-to-day basis, how do we actually advise management? And these are three approaches that we're using around the world. We've trained up groups around the world to help get these models up and going. So there's multi-species production models, there's the size-based models, and then there's the minimum realistic models. So for different ecosystems around the world, how can you use those to help inform fisheries management? In particular, there's across Southeast Asia, they love to use production models. The aggregate production models, where you lump all the species and all the catch together and treat as one superorganism, is quite often used, but they often only trust the last 10 years of data. So we've been working in the Gulf of Thailand, going through their data sets to actually, this has been really interesting. It showed that in their data, there were actually different apparent regimes of composition and different species that were characterising that. But if you fit the production model to those different time periods, you actually got different answers. And it's because they're different ecosystem structures that, having dug into it in model world at least, it's because they're different ecosystem structures at those different times. So they're up here now with food production questions. They say they want to recover the ecosystem, but what do they really mean? If they want to feed their population, what version of that world do they really want to get to? If you use EWE to optimise, you get through here. You can actually get a very similar answer to that just by recognising the different life histories. So separating, instead of by whole of fishery, say, okay, these are slow-living species, these are fast-living species. Separate those and combine them back after you've done the fitting. That comes out with a very ecosystem model-like answer, but it still doesn't get them away from having to face down which kind of ecosystem do they really want, and what are the inherent structural soundness, robustness of those different ecosystems. The other horrifying thing we found through most of Southeast Asia was that in trying to improve from the aggregate production model, they'd taken to fitting individual species production models and then just adding them together, without understanding that those peaks in ecosystem species happen at different times. So the sustainable biomass estimates they were getting out were 1.5 to 2 times higher than if you did this aggregate approach. So well above what was actually really sustainable by any metric. So having to undo what was a well-intentioned step has been a fairly significant effort. But you don't have to stop there. You can look at completely different ways of looking at how sustainable an ecosystem is. So this is a method that was originally developed in Australia but has now been used around the world, and it's just a method of triage basically. You're not trying to get to a quantified estimate for any of the species. What you're trying to do is just flag species that might be vulnerable. So by Australia's laws, we had to go through literally every species that interacted with a fishery. So that's actually over a few thousand. So how do we do that? We can't assess all of those. So the method was literally, the first pass was, is it at risk from the fishery in the first place? Low, right, we don't have to worry about you. Only medium to high, and if we had no data, you're automatically considered high risk. Then you took them up to the next step, which was to get more into their life history characteristics, their trophic interactions, habitat use, and then start to rate whether they were low, medium or high. And it was only the very high species that you had to escalate up to needing full quantitative assessments. So for instance, in one fishery that I work with, we went from 600 species at this level down to 25 at this level. We really had to get extra data on. So it was a very fast way of triaging both species and habitats. But you can also plot this level on these kind of risk maps. And so these are individual, they can be done for aquaculture farms. They can be done for individual species in an ecosystem. But the main idea is to plot out where the central tendency of risk is for the whole system, but also for individual species to say, okay, this can be productivity and susceptibility, which are different aspects of your exposure to fishery and your ability to recover. Or you can recast it with a slight tweak by saying, okay, these are things that we can't do anything about. These are things that we can do something about management-wise. How do we take the animals up there, or what management can move them down into these less risky areas? Or what kind of management can take us from here up here so that we can avoid it? So that you can start to, even at that level, say, okay, how can we start managing this system to actually make it less risky overall? Now, elsewhere in the world, they've moved on to cumulative ecosystem assessments, which really just boils down to all the steps of adaptive management stepped out through time for multiple sectors. So you're setting your objectives, you're finding your trends, you're setting which management actions you want to take, and then just seeing if they work. That involves looking at the connections, so they can be human industries, they can be ecological components, and getting them together. In Australia, we've been working on trying to get that spatial map. Piers Dunstan and Keith Hayes and others have started this work, and I've recently come into it as well. The most often used method around the world is just to additively say, here are all the pressures, add them up, get a map of where the pressures are. That doesn't deal with the non-linearity and uncertainty that's central to the way that ecosystems work, which is how I've come into it. So we've got to come up with a method that's still as easy as that map to communicate to the decision makers, but takes that uncertainty and non-linearity, because things that, if you're going to maximise your spend, if you've got a synergistic interaction where two things are making the situation works, you want to target that for your spend because you get a bigger outcome from your conservation action, for instance. You've got the system back further. You hit an antagonistic situation and you act on one of them, you can often make the situation much worse than if you'd actually left things alone. So trying to understand those is an important step we're taking. We're also moving into indicators and what that really looks like. Some work funded by LenFest has us looking at ecosystem and system level indicators of structure and function. So going through what that looks like globally. A lady called Ingrid Van Putten and Sarah Hornberg led the work for us. We're involved in looking at close to 200 papers, 134 we could do anything with, to dig down into what are the indicators that are already tracked, social, economic, institutional, largely around safety and profitability. Interestingly, of all of the papers we looked at, there were 2 papers that tried to link an indicator to an actual objective. So the whole point of having indicators in a management realm is to show you how well you're performing against that management action. That hasn't happened in the social indicators. They just report it like magic, as if someone's going to know what to do with it. Also interestingly is most of the papers that have been put out are in the Northern Hemisphere in Australia. There's very few through the developing countries, but they're actually the ones where they really are using social indicators. So in the project we were in, initially the funding body wanted to say, look, we don't really want the social indicators, and India said, no, we have to make decisions with these social implications front and foremost. So you really do have to take it, even if you have an eco bent to what you're trying to do. On the ecology side, there is literally thousands and thousands of indicators that have been put forward. Now the orange ones here are the kind of classes of indicators that are most often used, often around the status of the system. They're not really about the structure and function of the system. That's been a big missing gap trying to capture. The person who drew that beautiful picture in the top corner there is sitting in the second row, so make sure to embarrass him this afternoon when we go for drinks. I'll point him out. One thing we have done, wow, that's come out really well, hasn't it? The one thing we have done is try to put multivariate statistics. So taking the catch composition for different locations and just looking for how that changes through time. So if you can get surveys and match it, that's better, because then you know it's for real, reflecting what happened in the ecosystem. But even well, you know, catch can often be what you see. So just exploring it from that kind of side of things. In India, for instance, we really could detect the huge regime shift that happened inshore, both in terms of what they were catching, but what was actually in the water at the time. And in Australia, it's showed pretty well that we went through a system where we heavily depleted our fisheries, and now we've been recovering them. So it does seem to be able to reflect what we've been seeing in the system. So it does seem to be a useful approach. So that very empirical approach is something that's happening more and more around the world. So there was a recent paper that came out just looking at what total catch looks like versus total production, and putting some lines in the sand to say if you go past this, you're overfishing at an ecosystem level. And sadly, a third of the ecosystems of the world are already being fished at levels that are above those points. There's other methods to look at that. So you can look at cumulative impact or cumulative biomass versus trophic level or production curves. And over again, they show a similar pattern of how they change once they're perturbed. So you can start to use those as indicators. Interestingly, when you look at, and Link has recently, and Simone has recently published on this, most of the world's ecosystems thankfully still live in this section up here, though they are sort of heading in this direction. Those that have been affected have come down this arm. There's very, very few that go this route. So that's starting to help us understand the transition pathways that ecosystems go through, so we can start to set up understanding that pathway. You can also have methods to try and understand how much pressure you're putting on a system. So looking at all of the world's catches, there's models that have come out that have shown what are the major determining or correlative properties that match those catch, and these are the major things. You can then recast those into giving a pressure index, so you can show the relative pressure through time, but also through space, so you can start to help prioritise the actions that you're taking. Some more recent work has been about trying to bring a lot of the network theory, that's the world's network body of knowledge has exploded recently, has been growing through time, but really recently, and bringing that back to being more useful in ecology. So it was like there'd been the academic use of networks, and the real world, so to speak, the living world had applied it. So bringing that applied knowledge back into the food web side, you can see in a food web that evolution has optimized them to take production from the bottom and deliver it through the web as fast and efficiently as possible. They're also immensely robust to the random removal of species. However, and even that structure, you can tell from the patterns in what's connected to what even the dominant ecological processes are at any one time, whether that's predation, competition, environmental influences. Exponential random graph models can pull that out for you. We do know that stressing them changes that network structure, and some recent work by a gal has shown that you can, even looking at the density and the patterns of flow and connections in a network, can tell you how much internal resilience it has. So there's all of these properties that we can now look at just from the structure of the network to understand some internal features of fish systems. And in particular, we've been playing with this in that you can identify what's called a hub. So I said that ecosystems are really robust to the random deletion of species, but they shatter when you take out a hub species. And that was what, in model world, was causing that response that I was seeing, that there was a much faster loss of species if you fish selectively of the ecosystems than if you were fishing more broadly, because you were shattering them. By trying to be selective and minimise your footprint on the rest of the ecosystem, occasionally you were taking out a hub species, and that shattered the integrity of the whole rest of the food web and caused cascade failures. Now, interestingly for me, and this is some work I'm trying to write up and then it'll go to Ray Hilborn and it'll never get published, is that there's a tension between people who think you have to protect forage species and the people who think you don't have to protect forage species. In the initial analyses that I've done so far, it just so happens that the ecosystems used by those people who make the argument for forage species is that they're hub species in those ecosystems. The examples put forward in the other cases is that they're not hub species in those ecosystems. So both sides of the argument are right, if I don't deafen the audience, for the ecosystem that they're working on. So it's about helping people understand what kind of system they're in, so what kind of species need protection in those ecosystems. So trying to get away from that age-old science of I'm right, you're right, and actually find a useful way forward. Another thing to think about is, okay, how do you actually then manage an ecosystem? So growing up on farm, we had those massive old tractors that had a gazillion levers, that was how you steered. So if you think of each one of those levers as a gear, how do you set the gears across different fleets so that you have the ecosystem footprint that you want? So that's how to steer the ecosystem in the direction that you want, by pulling those different levers. So if you break them out, what's their combined footprint, and how do you set that to be the useful level that you want? And some work, this is actually a way that they manage a fishery, a very data poor fishery in Australia, and Keith Sainsbury's been generalising this in some work he and I are doing to help fishermen in the southeast of Asia, is it's not about trying to have infinite information about every species that you're after. You look at the ecosystem and say, okay, these are the ones that are going to be around classical reference points like B48. These are the species that are vulnerable. They're always going to be less than that target. You just can't have everything at the target at the one time. Know what they are. And then these species are ones that, for whatever reason, whether they're not market attractive or they're particularly robust or whatever, they're going to be higher. Now, pick the most vulnerable link in each one of those chains, so the most vulnerable robust species, the most vulnerable target species, the most vulnerable, truly vulnerable species, and track those, being representative of the rest. If they're doing what you want, then you're happy that you're staying in the place that you want to be. If they're not doing what you want, what's happened, what's changed? So don't get stuck in optimising just for those species. You do have to be careful they're really remaining representative, but it's a way of making it tractable. And it certainly worked for 25 years in the northwest of Australia, where they had very little information, but they've been able to sustainably manage quite a large number of species as a result. Another approach that I've been playing with was adapted from the Scots, who were going to use it in the North Sea till the Brexit madness started, and now they haven't had an opportunity. But the idea is that you fit a profile between biomass and production in an unfished version of the current environment. So it does require an ecosystem model. So you take the current climate environment, you run that in the model to see what that profile would look like without any fishing, and that sets the bounds of this green band. So it's basically the slope of that profile with the noise about it from that profile. Now, if you have species, it works out mathematically that if you have species that's sitting in there, the pressure on them isn't distorting the structure of that ecosystem. Whereas if you're fishing above that pressure, you're actually putting distortive pressure on the ecosystem, and you risk causing that fragmentation that we talked about before, where you shatter the web. If you're on this side, you've got space to increase. You don't have to, but you've got space to increase. So it's about not necessarily managing immediately to that, but using it as a laugh check. So in Australia, we've started this process just as an academic exercise to start off with. There was, how do the current quotas match versus this kind of situation? And it has been that when we were in a very overfished state, we had a lot of species out here, and in recovering them, we have been bringing them back down, by coincidence in this instance, back into this mould. But now we're looking at how to test harvest control rules with this as a secondary step. So you put up what's been recommended from single species, see how it's there, what kind of adjustments you might need to make to have that ecosystem perspective brought in as sensible bounds on a single species approach. We're also starting to look at true multi-species harvest control rules, and whether this is a useful approach, or Keith's indicator species approach or other approaches are a good way of dealing with that. The last bit of work I'd like to mention is something that I've again been doing with people in the audience here, which is to combine all of the components we have of structure and function that I've talked about into, it was basically inspired last summer because we had huge bushfires that got to within 10 kilometres of my place, and I had to spend a whole day brush cutting around my house in the vain hope that my house might survive. It did, thankfully. But in doing that, I suddenly thought, well, we have this fire rating system, and they bring together lots of different pieces of information to give us that fire rating. What if we could have an ecosystem rating? So bringing together all that structural and function information, yes, you can have it separately if that's your interest. In Australia and North America, we probably would keep it separate to understand. Places like India and Gulf of Thailand, they just want to know what their rating is. So can you bring it together sensibly? And we're still testing this, but it does seem to work. So if this is Southeast Australia and you go through this process, we went from yellow in the 1990s, up through to orange by the time we started to really depress our systems. And in recovering them, we've been bringing them back down until climate came along, and now it's messing things up nicely because it's changing the productivity. So if you measure versus the world back in the 1990s, we look like we're back in a sad state. But if you measure versus what's actually possible under the new climate regime, we're doing okay. We've got it back down, but we still need to be a bit careful. In the Gulf of Thailand, there's a really clear evolution since the 1950s where they massively changed it through those regimes I mentioned till they got to a really dangerous state. It was literally on the edge of what mathematically would have been said was a catastrophic collapse. Now, in their actions in the last 4 or 5 years, they've started to step away from that. So it'll be interesting. Interestingly enough, it's not unwound. It's not come back this way. It's heading off for another ecosystem state again. So ecosystems are very dynamic, and we have to think about whether the structures that we want are sufficient, or do we really want to try and reproduce species combinations of the past, and can we do much about it? Now, the last question I often get asked about ecosystem-based management is it's very expensive, or the assumption is it's very expensive. Is it worth all that effort? If we just did single species management well, would that be enough? So in some work we did where we simulated the whole of an ecosystem, and we had one version where we did lots of very data-rich assessments, one that was where we only had data poor. We did a version where we had multi-species harvest control rules, and we applied that over a whole bunch of species versus just a small number of selected target species, which is more like the reality. We had versions where we did full integrated ecosystem-based management, which in a model world you can do. Reality will be a lot harder to do, but in the model world we could do it, versus just single species management. And we also looked at the case where what happens if you can only manage part of an ecosystem. So you've got, just say, a border. So we put the border within Australia because we didn't then have to worry about pissing off any neighbour country, but just looking at if you put a border between two different states and one state was managing and the other state wasn't, what were the implications? What we found was that no management, as you might expect, is the absolute worst outcome across social, economic and ecological objectives. Ineffectual, so you went no management, ineffectual single species, ineffectual multi-species, good single species, good multi-species, good ecosystem management, even if you could only manage part of the system. So it really does pay off in terms of social outcomes, economic outcomes, environmental outcomes, and in particular opportunity costs. So it looks expensive in the short term, but in the calculations we did, 99% of the cost of a fisheries action are in what's called opportunity cost into the future. So what looked like an expensive event now, it saved you an enormous amount of losses into the future. That's still a very hard argument to make in a fishery where the fishermen have to pay for the management, which is the case in Australia, but at least it gave us some discussion points. So it is actually possible to get there. It's going to look way more like this than like this, but you can actually get to some ecosystem-based management outcomes. So it is a very challenging time, but we should embrace that. And one of the very first lessons I learnt about modelling was actually from Carl, which is you want to embrace complexity, so have that dynamic outcome, not complicatedness. So it's not about adding excessive detail or excessive rules. It's about getting the shape right with the minimum amount of effort, basically. So we can do that both in terms of the tools that we use, but the management methods that we embrace. So the tools exist. They are transitioning through time about what they'll look like, but they are out there. Another modelling lesson that I've learnt that I think applies to life and to how you do management is it's not just about what you bring in and put in a model, it's what you explicitly leave out. So in leaving something out, make sure it's a considered opinion, not just something that happens by accident. And that's equally important for when you're setting objectives in a system. Importantly, after having modelled about 98 ecosystems around the world now, I know there's some common features, but there's not one single way that an ecosystem works. There's not one way a social ecological system works. There will be different answers in different locations, and trying to find a single or impose a single answer is not going to really get there. And most importantly of all, we've got to continue to learn adaptively. So we're still going to be driving by looking in the rear view mirror, but we can start to have a peek of what's ahead of us. And it's not perfect, there's still lots of different futures out there, but hopefully it'll let us spot some of the biggest dangers that are right in front of our face, so that we don't have some colossal stuff up. So I've got to remember not to swear when I'm outside of Australia. Colossal mess ups in our immediate future. And if I can get this to work one last time. First, I have to acknowledge everybody. There's a huge number of people that I've collaborated with over the years, and they've all contributed to that thinking and a lot of the science that you're seeing. And more importantly, there's a young lady in Australia who was struggling with her own life balance, and she's created an enormous resource for people to actually go and look at how to make kids and life work in academia, which isn't an easy challenge. So I'm going to give a gratuitous plug to Kirsty's stuff as well, but that's it in a nutshell.
See why she intimidates me?
Should I just take that as a statement?
Yeah.
Thank you very much, Beth. That was a really illuminating talk. Thanks. I just wanted, first of all, I was very interested in your idea of hub species, especially because when you first showed those plots of the selective versus non-selective curves, it seemed counterintuitive to me. And so, you know, we're quite sort of proud of the fact of making our fisheries more selective by putting the right incentive systems in place, for example, to avoid choke species and that kind of thing. So now we're learning, I've just learned that if you focus too hard on a hub species, you might collapse your whole ecosystem. And I just wondered how confident you can be in an ecosystem of identifying those hub species and how you go about knowing. You would need an ecosystem model, I guess, but given the paucity of data.
So you don't necessarily need an ecosystem model. What you do need is good information on what's connected to what. So we've done it large. So the most robust has been from fairly complete diet sets, which are obviously very rare as time series around the world. It has been successfully able to work, and I believe there's a paper not by me but by Simon Levin, Martin Schaefer and others coming out in Nature Climate Change the next little while, where they've used exponential random graphs based purely on expert-based information from ecologists in the Arctic to track change through time up there. So there's a whole bunch of people that are from different directions, all are coming to the same conclusion, and it looks reasonably robust to being able to use expert information. The problem is time lag, so if it's just on experts, so if we think of the Gulf of Thailand and those shifts through time, you could potentially get on top of that fairly rapidly with survey or diet information that was contemporaneous. Just relying on experts might mean that you're a little bit lagging in realising that system structure's changed, and so the hub species may have changed. So there's never going to be a bomb-proof approach, but it's just one other piece of information to bring to the table to flag, okay, this is something else to consider when you're thinking about how you're spreading it. And in terms of fishing an ecosystem, it's not necessarily, like I said, about going hell for leather on absolutely everything, but a good analogy is when you cross ice. You don't want to put a lot of pressure in one exact spot. You want to spread your pressure gently over a larger group. And that's the kind of analogy that, at least in model world, and I will classify everything as model world, I live in model world, in model world that works to be sustainable. The proof is going to be in pudding about whether it really works in the real world, but as a first effort, it seems to be a more sustainable approach. Now, how you do that mix across species, again, I don't think there's one clear solution. It's obviously had quite an exciting debate around a couple of topics more recently, like balanced harvest. Whether that's actually even technically feasible, I'm not sure. But yeah, just rethinking about, with all the best of intentions, we've been giving advice in one direction for 30 years. So we need to unpack and rethink about the kind of advice we're providing going forward.
I enjoyed your overview of human psychology. I was wondering, how are you using that not just with your kids, but with other scientists? Do you find, you told us about it, I assume you feel it's important?
Yeah. So it helps you on a personal level understanding conflict and how to step away from it. And so one of the biggest things that you find is that when people have arguments, understanding why an argument's come about And largely psychologically speaking, it's because we all in our heads assume that everyone else in the world has exactly the same vision of the world that we do. So if we're disagreeing, it's because the other person is a complete prat, because obviously he knows the same things I do, so, it must be just his personality. That means he's come to a different conclusion. Actually, the models aren't the same. So it's understanding those different views can help unwind those arguments, but also embracing working with a broader set of people who can bring those different views, who have a different set of conditions in their teaching, so that you've got those alternate viewpoints. So whether that's different classical academic disciplines or traditional knowledge holders. So when I went through university, you weren't to talk to people like traditional knowledge holders because what they had wasn't scientific, but having that alternative worldview can be a very different way to, okay, that's a different way of looking at it. What does that bring to the conversation, particularly if you integrate it from the start? You want to have a tiramisu of different disciplines, not a cherry on the top that's an afterthought. You want to actually integrate things a lot more evenly, and that's where it's coming. It's valuing those different worldviews and even the fundamentally different way that social sciences think through a question, which as a mathematician and biophysical scientist often have to go, I just need to go for a short walk for a second. It's like, there is one proper answer, 2 and 2 is 4. It's not about the journey. Come back in, yes, okay, I'm happy to be adhering there. So there are some struggles there past.
The plots you had for the changing conditions, was it PCA?
Yes.
Could you elaborate on the axes?
So they're just principal components analysis. So taking the catch composition as resolved as possible from these locations. So they will often record, they might only tell the FAO some large chunks, but if you work with them, they will eventually give you out more finely detailed ones. So you run the PCA on literally the volume of catch per species through time. You usually find there's only 2 to 3 components that are important. I've yet to find more than 3. It usually falls out in 2 so far. I've done it in about 40 systems around the world so far. And so far, it's being careful of the fact that we like to tell ourselves stories. So far, it has lined up with either survey information or expert narratives around, oh yeah, that's when the system changed. And in some cases, it was because there was a major new technology introduced. But that was often, when you talk to the old guys who were around at the time, it was because something else in the system had failed and changed. So they'll bring in the new technology to make up for it. So you do have to be careful that it's not a market effect or a human faggot effect. But so far, those very large changes have all been around significant compositional changes in catch and ecosystem in the places that we've looked so far.
We have time for one last question. Once again, we'll have 2 last questions.
So we
All right. So what would your advice be? Like first piece of advice each a researcher who's wanting to set out and communicate their science to managers?
Please repeat the question.
So he wants to know what's the first piece of advice when you want to communicate with the manager. Find a small child. So the reason I say that is because we spend 10, 15 or more years learning a different language when we come to university. We get academies or sciences or whatever. We forget how to speak our native tongue. So it's worked very well for me it doesn't work so well now that they're big, but when my children were small, if I could run through a talk with them and they could come back to me with, okay, your major points were blah, 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 I knew I had pitched it well. And it's not because policymakers are idiots, it's just they have so many other things on their mind that you've got to be able to get it across in a simple way that they can pick up, almost in despite themselves. With every other thing in their head, they can get the simple message. So keep your message simple. Even if the work is complex, you can always tell as an editor what's a paper that's come from a PhD student because they have infinite detail on every little work they've ever done. Whereas the very old professors kind of told you, yeah, he came in, he did that, here's the answer, done. A little bit of that is complacency or excitement, and a little bit of it is because they've learned a different level of communication, and that's pitched to your audience. So if you've got a technical audience, they're going to want the technical detail. So it's that hidden problem. Come out with a simple answer, allow them to dig for extra information if they want it. Don't hide things from them, but don't hit them with all that from the start, as much as you want to love it. Yeah.
Okay, last question.
Thanks for the presentation. always as good. My question is about climate change. So we know that we all work and all the models that we are working are based on a reference period of the past. And we know that the system is shifting faster than we think. Species are moving. Some species, their population is already collapsed. And the problem is that we are using the EBFM models, so Atlantis, EWE or whatever, based on what we know. But the problem in management is that we're going to figure new problems that we don't even know where they come from, with new species gain, invasion. Do you think these models that we are working on can solve some of these problems?
They can certainly help you give some insight. So you can play out those potential futures. You can add climate, you can add invading species, even just as a theory about what could happen. So it's about joining different kinds of knowledge. So we're very good at predicting for a state if we know what that base state is. We're not very good at conditional statements. So the great one to as an example here is Genghis Khan. So there was a whole bunch of droughts and then it got to be nice climate. You could predict from that there would be an expansion of the Mongolian population. It roars through Asia, Europe. At that point you could see that the Middle East had been destroyed, so that left a power vacuum. You couldn't predict that there'd be a heart attack and every Mongol would have to go back to Mongolia to elect them. They had a vote. They knew what the vote answer would be before they even left Europe, but they had to follow the tradition. And so once you know that that's happened, then you can say, okay, the power vacuum lets you predict that Europe would take off because the Middle East, even 800 years later, is completely stuffed as a result. So it's that contingent event you couldn't do. You can do either side, but the contingent event trips you up. We're not good at predicting those. So what you do is you marry your models, you put in as much dynamic processes like evolution and stuff like that that you can cope with sensibly. And then you use scenarios. You get people to come up with ideas of what might happen in the future. You chuck those at the model. So the human brain can be the inventor of the contingent event. And then you can try out ideas for consistency in the model world you have. So you can use qualitative models to do that really rapidly. You can play it out in dynamic models to see, okay, we can't cope with that. So there's a whole bunch of the climate models to do with economics that predict a certain amount of change. But when you unpack those economic models, it's because they've hit the bound of the amount of change that that model can ever produce. So it's a bit like Chernobyl, where they all said, oh, it's only been this level of change. That was all they could actually record, even though it was this level of change. So you do need to understand the bounds of the model type you're using, but then use the human imagination. So work with people to chuck those alternate scenarios, like contingent events, at you to broaden your thinking. You're always going to have the vampire in the basement, as Carl calls it, which is the hidden thing you hadn't thought about that comes out to get you. But you can try and arm yourself as best as possible, given your best available information. How can you explore that space? And then be willing to do it again when you get some new information. You're not going to ever have a simple cast-on answer that's going to hold forever.